Next, we will have an oral presentation by Rui Zhao presenting energy-based hindsight experience prioritization.
Hello, everyone. My name is Rui. Today, I gave a presentation about our recent work, energy-based hindsight experience prioritization. The work was done at Siemens Munich under the supervision of my professor, Volker Tresp, from Ludwig-Maximilian University of Munich. So this work is about sample-efficient reinforcement learning in robotics. We know that reinforcement learning algorithms requires large amount of training samples. For example, in video games, the agent normally needs millions of frames to train with until it is get good at the game. However, to collect such large amount of training sample in robotics is very expensive. So the goal here is to improve the sample efficiency and without increasing the training time. Our work is based on the previous works, including the deep deterministic policy gradient and the hindsight experience replay. So we first formulate the robotics task into a Markov decision process. And we can train the agent with standard reinforcement learning algorithms, such as the DDPG. Deep deterministic policy gradient is essentially an off-policy actor critic. The actor network learns the policy directly. The critic network approximates the Q-value function. So during training, the critic network is updated based on the actions selected by the actor network. And the actor network is trained to maximize the approximate Q-value function by the critic. And in 2015, Zhao and others proposed universal value function approximators. So this method generalized the policy to goal states. So now the Q-value function is not only depends on the states and actions, it also depends on the goals that agents wants to achieve. And very recent, in 2017, Andreas Vasky and others proposed hindsight experience replay. So this method encourages the agent to learn something instead of nothing. And it shows promising results in sparse reward environments. However, this method replays the sampled trajectories at random during replay. And the more sophisticated replay strategies are requested, as mentioned in the work of Plaperis and others in 2018. So our hypothesis is that trajectories with higher energy involved is more valuable to learn from. And this hypothesis is based on the work energy principle. So we know that in physics, a force is said to do work. When acting, there is a displacement of the object in the direction of this force. And based on the work energy principle, we can calculate the kinetic energy change based on the change of the velocity of the target object. We are interested in the energy increase of the target object from one state to another state, and we refer to this as transition energy. We define the trajectory energy function as the sum of the transition energy of the target object during the complete trajectory. So first, let's have some intuition about this trajectory energy function. So in the first case, the robot arm has no contact with the target object during the whole trajectory. So there is no work being done from the robotic to the target object, and the energy of the target object does not increase during the whole process. In this case, the trajectory energy remains zero during all the time. In the second case, there is some interaction between the robot arm and the target object. So there is some work being done from the robot to the object, and the trajectory energy is larger than zero, and it's still not very high. And in the best scenario, the robot arm successfully manipulates the object during the whole trajectory. And in this case, the trajectory energy has the highest value. So now we formally define this trajectory energy function. First, we calculate the potential energy of the target object, which equals to the mass of the object multiply the gravity of the Earth and the height of the object with respect to the ground. Secondly, we calculate the kinetic energy of the object. We can approximate the velocity of the target object based on the displacement of this object in a certain time interval. And we calculate the kinetic energy in the x, y, and z direction and sum them together so we get this kinetic energy. And similarly, we can also calculate the rotational energy of this object. So in this simulation, we have this Cartesian representation of the object's orientation. We first convert this Cartesian representation into Euler angles. And based on the Euler angles, we can approximate the angular velocity. And afterwards, we calculate this rotational kinetic energy in the three directions and sum those terms together to get the rotational energy. The total energy of the target object equals to the sum of the positional energy, the linear energy, and the rotational energy. And we define the transition energy as the energy increase of the target object from the previous state to the current state. So here we're only interested in the energy increase because this increase can only due to the work done by the robot to the object. And we define the trajectory energy as the sum of this transition energy over the complete trajectory. Now we propose the energy-based prioritization. So we use the value of trajectory energy directly as the probability of this trajectory to be replayed, which means that the trajectory with higher energy involved is more likely to be replayed during learning. And note that here we only use the trajectory energy to prioritize the experience and not for assigning rewards. So therefore, a bad trajectory with very high energy will still be discouraged based on the negative rewards. This is the complete training algorithms. So basically, the agent first collecting the experience with other trajectories. And afterwards, when a new trajectory is available in the memory buffer, it calculates the energy of this trajectory and prioritizes its trajectory based on energy for replay. And afterwards, the model is updated to use off-policy reinforcement algorithms, such as DDPG. So our code is on GitHub, and you can find the link in the paper. We also compare our method with prioritized experience replay. This method was proposed by Shah and others in 2015. The motivation of prioritized experience replay is to prioritize the transitions with high energy. However, this method is very expensive in computational time. It needs to update the priority in the memory buffer after each model updates. And in our experiment, for the hand manipulation environment, we need to train the agent for 80 hours to complete the 200 epochs iteration. This method improved the performance. And on the other side is our energy-based framework. So our motivation is different. We want to prioritize the trajectories with higher energy involved. And in the experiment, there is no increase of training time. The reason is that the agent only needs to calculate the energy of this trajectory once when a new trajectory is available. And in the experiment, we only need to train the agent for 8 hours to complete the 200 epochs iteration. And still, it gives a better performance improvement compared to prioritize the experience replay. And those are the 4 robotics simulations we used in our experiments, including the pick and the place task, the hand manipulation of block, egg, and pen. So those environments are provided by OpenAI. To compare the performance, we calculate this mean successful rate with respect to epochs, and we conduct the experiments with 5 different random seeds and average them. We show here in the figure the mean value and the standard deviation. So in our 4 tasks, the energy-based method gives the best performance. And after training, we use the best learned policy and test it in the environment. We get this final mean success rate. From this table, we can see that the energy-based method improved the performance by 4 percentage points on average over all 4 tasks. We also list here in the second table the training time of different methods in the environments. We can see that the energy-based framework consumes the same amount of training time as the baseline method, Hindsight Experience Replay does. However, the prioritized experience replay consumes double the training time in the pick and place task, and consumes about 10 times the training time as the baseline does in the hand manipulation tasks. To compare the sample efficiency, we get the number of the training samples required to reach a certain test accuracy. For example, in the first figure, pick and place task, to reach the same 93.8% test accuracy, the baseline method needs about 93,000 training samples. The energy-based method only needs 48,000 samples. So in this case, we improved the sample efficiency by a factor of 1.9. And overall for task, on average, we improved the sample efficiency by a factor of 2. We also investigate the Pearson correlation between the trajectory energy and the TDLs of this trajectory in the middle of the training. And on average, over the 4 environments, we have a Pearson correlation of 0.6. So this means that the trajectory energy is highly correlated with TDLs. And so it proves that higher energy trajectories are more valuable to learn from, and it makes sense to prioritize those trajectories because it accelerates the training. And then now let's watch a short video. So on one side is the energy-based framework, and the other is the baseline. And after training 10 epochs, the energy-based framework is about 15% better than the baseline. So it improved the sample efficiency. And in the second hand manipulation block task, it also improved the sample efficiency as shown here. So that's all. Thank you for your attention. Any questions?
There, yep.
Thank you for the presentation. I see why, I think I get the intuition for why energy is a good prior for exploration, because you're prioritizing exciting the robot's joints to like the full extent they can. So like rather than motivating exploring the full position range, you're going to excite the dynamics in a particular way, the light exploration. Do you think that's an accurate intuition? It's like similar to, I think, old methods for SysID, where they like intentionally try to explore in a certain like frequencies. Okay, so my real question is, I think my concern is in cases where you're penalizing or constraining energy, and this would eventually, you would plateau learning. Particularly if it's a sparse reward setting, you would, and if you had a small replay buffer, you would eventually kick out states with high Q and high energy and low energy, which is actually what the states you're trying to get to, right? Or is that also incorrect?
Yeah, in some sense you are right. And I mean the method, like to first find the samples which including the correlation between the movement of the robot arm or hand and the movement of the object. So if there is no energy involved, there is no correlation. So there is no pattern for the agent to learn from. So we want to find samples that involve this, have this pattern, and this also proves in the experiment is improve the performance. So yeah.
Greg?
Thank you for the talk. So it seems like one possible hypothesis is that the energy-based method, as you said, like makes it more sample efficient, learn faster. But it also seems like you could be providing extra information, like it's implicitly giving the location of the object and the position. Do you have any intuition about whether it's the energy formulation or the additional information that's giving the improvement?
Yeah, so here we actually doesn't require any additional information. So we only use the same information from this simulation, which already provides the position of the target object. And we only like provide this formulation to calculate the energy. And I think this formulation for calculating energy is general for all robotic manipulation tasks, because in the physics world, you can calculate energy anywhere. Yeah.
Okay, let's take one more question while the next speaker sets up.
So thank you for interesting presentation. So this seems applicable for manipulation tasks,
Yeah.
right? Could you generalize it to movement or motion?
Okay.
Like, I don't know, yeah.
Okay,
Of
so
cheetah.
yeah, so the current work, yes, indeed, only for for robotic manipulation tasks. And if you want to use this energy method for general movement tasks, maybe you can track the inner energy of this robotic, like for each joint and arm. Yeah. So.
Maybe one more quick question.
Yeah, so I'm surprised to see how slow prioritized replay is running. And so are you updating the whole buffer at every step?
You mean for prioritized experience
Yeah,
replay?
for the prioritized experience replay.
Yeah, so to combine this method with hindsight experience replay, we only condition the value function based on the achieved goals. So we prioritize this based on the achieved goals, not to select which goal is more valuable to learn. Yeah. Okay.
Let's thank the speaker one more time.
Thank you.